Ooh, it's going to come off. It just came off. Okay, well, carry on as far. Can you all read this in the back? No. Well, the top line says hypothetical value of an asteroid. That's the top line. Small print. Asteroids could be a valuable source of metals. In 1994, William Hartmann of the Planetary Science Institute estimated the value of a 2-kilometer wide metal rich asteroid with composition nickel, platinum, cobalt, and iron. And he thought it would be worth $25 trillion. That's in 1994 dollars. And the largest mass would have been nickel and then followed by platinum. Now, I wonder where, in which planet they found that. That's an interesting question. And at that time, the U.S. debt was 15.5 trillion, so this would have been worth enough to pay off the U.S. debt. Okay, well, we'll pass on, except that I would like to mention that in 1994, platinum was in great demand, both for the then burgeoning fuel cell industry and the, of course, then burgeoning tailpipe control industry in the auto industry. I think since then the demand for platinum has possibly declined somewhat. Anyway, the first point I want to make is that there are half a dozen, maybe 8 major industrial metals which are mined for their own sakes. And you all know them, and I won't list them. There are a couple on the margin. One of the ones that's on the margin would be nickel and cobalt. They tend to be found together, actually. But mostly these metals are mined in mines where the ore is a highly concentrated form of that particular metal. Now then there are other metals, about 60 of them, well, other elements I should say, in the spectrum. And I think it's fair to call them hitchhikers in the sense that they follow an attractor metal in the metallurgical universe. And the hitchhikers are geologically rare. They're chemically related to one of the attractors. That's how they get to be there, where they are. You can see that in the periodic table if you want to take the time. They are found in the ores and the wastes of the attractor metal. And you've seen this several times already with different versions, and this is not a very good one, so I'll skip it. Here we see a better diagram showing rock-forming elements in the upper left, and the rarest metals down on the yellow area in the bottom, and a number of others of interest that are in blue. What are the blue ones? Those are the rare earth elements, blue, and the red ones are the elements that are mined for themselves. That's the industrial metals. And this you cannot read, I know. What it shows is that each of these categories of scarce metals gets used in a number of different applications. Isn't that a great insight? But the details are interesting, and if you could send me an email, I'll send you a copy of this diagram, or it is published actually in one of my papers, maybe more than one. And here you see the functions of the various hitchhiker metals, and again, each of these functions is served by a wide variety of the hitchhikers. And again, it's far too complicated to read from the screen. And if you really want to see it, as I say, it is published, or I'll send you a copy. Now here's the point, I think. The product life cycle of these major industrial metals vis-a-vis the hitchhikers that come along with them. And again, the printing is too small to see, but if you look over in the far to the left, in the middle, you see raw materials production. That's the primary metal, and right next to it, in the next box, is raw materials production of secondary metals. And then the metal initially goes up on the diagram to a product manufacturer, and there are losses in every one of these things. The product manufacturer metal demand is governed by product design, and thus couples between minor and major metals, the coupling between minor and major metals has disappeared. So anyway, these products go to use, and then they go to the end of life phase, EOL. And in principle, they would be recycled, but in practice, hardly at all. And in every one of these phases, you see losses, and the losses are, in the case of the hitchhiker metals, on the whole, very close to 100%. And that's a tragedy, because the future, as you heard this morning, the future of our industrial technology in the the end of this century at least, depends very much on these metals. And to go beyond this century, it's not at all clear what we're going to do. We could talk about that, but that's kind of another subject. Anyway, implications. The increased output of hitchhikers can be achieved only by more efficient processing of the primary ore. That's the ore of the major industrial metal that's being mined. That may require major and costly process re-engineering. It doesn't come easy. That's why it's not happening. It also means that higher prices for the hitchhiker in the short term are unlikely to yield increased output, unless there's an easy way to extract the hitchhiker from the mine or from the smelting waste. And this illustrates how the prices of these metals bear very little, if any, relationship to the production. Again, the details are impossible to read from the screen, and again, it is published. And again, the implications. It also means that order of magnitude increases in applications of some hitchhiker metals will be very difficult to achieve because of scarcity. Let me say that again. Some very interesting and productive applications are not happening because the quantities of these metals are not being produced, not large enough, not being produced enough. And yet, that doesn't mean there isn't enough metal around. It just means it's not being produced. Another way of saying it is that these metals are terribly underpriced. They're not being produced because they're underpriced. And they're not being recycled for the same reason. Examples: thin film PV using indium, selenium, or tellurium. You heard about tellurium already today, and I've got some more on that. Hybrid or electric cars using permanent magnets, and also this applies to the wind turbines. And curiously enough, only a tiny fraction of the wind turbines actually use these permanent magnets. They could, but there's not enough of the neodymium, which is a heavy rare earth, to utilize at the present time. If we were clever about recovering the stuff that's in the ore, we would be able to build more of those wind turbines. LED lighting, rare earth phosphors, europium, gadolinium, yttrium, lanthanum, cerium, and more. But this, as I say, the scarcity is mostly artificial. Gold and platinum are geologically very scarce, but they're not economically scarce. Why is that? It's a question of price. If the price is high enough, the metal will be recovered from existing ores, or new ones will be found. As in the case of gold, they're finding new ores all the time. And yet it's extremely scarce. If the price is high enough, any metal will be recovered and recycled. So that's a fact. So scarce metals are underpriced. Higher prices would justify R&D on new extraction and refining technologies, as well as new collection and recycling technologies. It is just a question of money, which is not scarce at all. The central banks of Europe, the United States, and Japan have been printing money. There's a lot of money out there. Apple, just to name one, has plenty of money that doesn't know what to do with it. They've got an estimated $250 billion in money overseas, offshore. And you go on to the others, Google and Microsoft, and they all got lots of money. They just don't know what to do with it. How many of you know have a good idea what they're planning to do with it? How many of you think that they're going to raise wages? I didn't see a single eye. Yeah? Oh. Who knows what they're going to do with most of it? Really? Oh, nobody knows. Well, they're going to buy back their own shares. That's what they're going to do. 2/3 of that money is probably going to be spent on buying back their own shares to raise the price of the shares, to benefit the CEOs and the higher executives, all of whom have contracts based on the price of the shares or something that resembles that. And I don't have a graph here to show you, but I can tell you, I can do it on the blackboard. This is worth seeing. Okay. Right. Okay. Well, I got a cell phone in there. Okay. Yeah, you ought to see this diagram, I think. Okay. On this axis, you see growth rate. I'll just call it rate. And on this axis, you see the fraction of current market value that the company has spent in the last 20 years on buybacks. And there are quite a few companies out here that have spent more on buybacks than they are worth today. Xerox, for example. HP, for another. IBM getting close. Well, they're moving in that direction very fast. And over here, the companies that don't do buybacks. Amazon, Google. Apple's already down the hill here somewhere, going fast. Okay. That's reality. This is what has happened in the past 20 years, and it's what's going to happen in the next 10 or 5. That's what the companies are going to do with their money that they don't know what to do with, that they're not putting into R&D, they're not raising wages, they're not paying off debt, they're buying back shares. The second major use will be to increase dividends. After that, whatever. Okay. So, Apple has plenty of money, doesn't know what to do with it. And the others, same story. They and others will use it to buy back their shares. That's a bad idea for several reasons. Buying scarce metals and storing them for a while to allow the price to get high enough to justify recycling would be a much better use of the untaxed money sitting in tax havens around the world. It's just a long-term investment instead of a short-term investment. And that, I think, is something everybody needs to think about, because right now the whole stock market, the whole economic system is totally focused on short-term, fast bucks. And that's a problem. Someday the scarce metals will be rented, in my opinion anyway. I think they will have to be rented rather than sold. It's the only way to really keep them from being lost. So that's what I think long-term sustainability means. And so here's a thought. What about using these scarce metals, a basket of them, could be quite a different mixture, where the gold, in the way that the gold standard operated for a century. It operated pretty well when it was working. It kept the money, the global money supply, or the money supply of the Western countries at least, from rising too fast. Once there was a gold standard for paper money based on trust in its inherent value, the paper money's been around for a long, long time, especially in China. This trust survives and keeps the price of gold so high right now that most of it is still stored, notably in the dowries of Indian women. That's about 2/3 of the total amount of gold, I think, that's ever been mined. It's sitting now in the bracelets, necklaces, and so on of women of India. Well, that's an interesting use. But the value of a basket of rare e-metals has a much more modern and more secure basis for being used as a standard for global money. I propose a serious study of this possibility. The Bank of International Settlements, BIS in Basel, might be willing to undertake, or at least to participate in such a study. And this, I could go on to the case of tellurium, but I think I'll stop here. I think this is a point where I think it would be really interesting to hear what you guys think. I'm done. We got 5 extra minutes. Wait, whoa. Oh, I'm sorry. I might have something else to show you. Okay. Well, this is kind of a closing comment. The current economic system, based on extraction of scarce physical resources, embodiment in products destined for brief use, followed by disposal, is clearly unsustainable. I think we all know that. Increasing efficiency of recovery and use can satisfy increasing needs in the short term, yes. Renovation and reuse are helpful, but recycling in the conventional sense, starting from a consumer or industrial wastes, is way too inefficient and too costly. So I think a new recovery paradigm is needed. And there you see a diagram form the sort of circular economy in green, and what we have actually the combination of green and red with a lot of red. And in the future, a closed cycle manufacturing system will be needed. This will require name brand companies that design and produce final goods such as Apple, Nokia, Sony, Siemens, Samsung, you name it, to redesign their supply chains. And to do that, some legal entity must retain ownership, or at least in my opinion, must retain ownership of the rare metals from cradle to not to the grave, but beyond the grave. In other words, just retain indefinitely the ownership, the actual ownership of these metals. And that, I think, is part of what needs to be discussed. And so now I'll stop.
Okay, I have a quick comment. You may be interested in knowing that about asteroids, there will be a conference on space mining in Italy in June in Milano. I was trying to find the coordinates, but it doesn't work. Too much technology. Maybe we're missing some tellurium in here. But if you are interested in this, contact me. I can give you the coordinates of this idea, which is sponsored by the aerospace industry, and they are making it clear that they are not planning any asteroid mining to bring metals to Earth. That doesn't work. But they're studying asteroid mining with the idea of using the materials to support everything which is being built in space, to support space expansion, satellites and power stations and exploration on Mars, etc. And my personal opinion that asteroid mining is kind of expensive, as you may imagine, but for this specific purpose, it may be less expensive to mine the moon or an asteroid than bring the materials to space from Earth.
Yes, just another comment occurred to me in reference to the discussion earlier about the difficulties of recycling when you have to make feedbacks. The fact that the industrial processes involved, especially in making microprocessors and thin film PV systems, require such purity and such purity of products that it makes sense maybe to produce them in a vacuum. And there we are. If we go to space, we might have a different reason for going out there is to get access to a high value vacuum without having to pay much for it, except once you get up there. And okay, that was just another random thought.
Hello. I won't comment on the asteroid mining, but about the end of your talk, it seems that you propose only market-based solution, like buying the metals to make them more expensive and triggering more recycling, or renting out private companies renting out metals that they have bought before. What about non-market-based solutions, like right-based approach, and the government would, for example, own these type of companies that make cell phones and laptops, and would, it seems very, very planified, but it could be sensible that each adult has a right to use one computer that he doesn't own, but he has it's given, it's lent for free, and so on and so forth. Like he has to give it back, or when it's broken, he blah blah. Like
Yeah, well, in a way, I agree with your point that given the characteristics of the companies that are making lots of money today, I wouldn't want to trust this to them. But on the other hand, the governments aren't in much better shape either. What I would like to see, and I don't know how to do it, would be to create some kind of international body which would have to be very trustworthy. And that, I don't know how to go about doing it or even thinking about it, but it shouldn't be really Apple doing it or any of the existing private companies doing it. It should be something much more international and something much more trustworthy than any of those. And yet it should be done. I mentioned the Bank of International Settlements, which is an international organization, and it does have a fairly good reputation, and we might start with something along those lines.
Klaus Lackner, I have actually two questions. The first is, with the cadmium telluride, I understand that you can retrieve it because this was predominantly cadmium telluride. I actually personally am nervous with gallium arsenide, cadmium telluride, whether I really want it out in the open where a hailstorm or a sandstorm or a fire can spread it out. But that's a separate question.
That's a good reason for not letting it.
For not having it there in the first place, right.
Yeah.
But if you look at a lot of the electronics, you are mixing this in at parts per million, and you will have to get it back out if you recover it. So your lease or your lessor has a real problem recovering.
Sure.
So how do we fix that?
Well, that's a very technical question, and I'm willing to talk about it. I'll say just this much, that if you're trying to get all of them out, it makes much more sense than if you're trying to get one or two of them out.
Yes.
Right now, part of the reason why the whole system is so inefficient that the only thing that people really go after is gold, or gold and platinum, and the rest are left alone.
Then
But if you had a recovery system involving very high temperature melting and so on, I think maybe a new technology that got all of them at once rather than one at a time. would make
So the answer is a technology which
Yeah,
can
oh, yeah.
actually separate everything.
Sure.
Then my other question is the electronics industry has been notoriously fickle in what are the right elements to use. So if you now say gallium is in my mix, what happens if technology bypasses gallium?
Well,
So
I
is
think-
is it secure?
again, looking at one at a time, you run into more of a problem than if you go for the whole basket. And I would think in terms of a basket. And maybe they'll be shifting around within the basket, but that would be my answer.
Are there any other questions?
You all want your drink, I know. That's
Okay, now you can meet Grégoire Chambaz, who is a researcher and learning assistant at Haute-Savoie École de Gestion in Geneva. He will present us his work on the collapse risk from an energy perspective, an introduction to the works of Joseph Tainter.
I hope everybody understood me well. And I'd like just to add something. Geneva is in Switzerland, not in Haute-Savoie, although I really like French cheese. So, first remark. The presentation I'd like to do with you today pertains the risk of collapse, or maybe the scenario of collapse, with an energy analysis. There has been more than one theory pertaining collapse and how collapse may happen. I surely do not know for sure what works and what doesn't, but we can explore together one of those theorists which issue a theory that maybe withstood the time better than others. As you may know, there has been 220 sole explanation for the collapse of the Roman Empire, and they are all competing together. So maybe tonight you will be convinced or not, this is a presentation, by the explanation proposed by Joseph Tainter. There has been other collapses like Mayas or the Eastern Islanders, and we will try to from an energy perspective and a resource-based perspective to know exactly what can happen in a big system. And this is a kind of model, and as all models, they are not perfect and they should be criticized, but without models we are unable to describe reality. There has been more than one possibility to represent collapse, and there are mythical representation. We try in that presentation to go away from the myth and to try to quantify or to exemplify what can happen. There has been also a lot of different typologies of collapse. As I said, there has been, for the Riemann downfall, more than 220 explanation. There is just some of them that are shown right now. And recently, 10 years ago, another kind of explanation which was brought by Jared Diamond got huge mediatic impact. And what Jared Diamond said in his book is basically that the collapse risk can affect all society, especially when they are subject to environmental constraints and that they are unable to respond to them. And he got really a huge audience, and this is really interesting because he was then really contradicted by archaeologists, which refuted all the examples he used in his books, but still its explanations remains today as one of the major explanations for collapses. And this is something we have to be very careful with collapses, because this idea is for some of us so huge that and the challenges of today's civilization may be perceived as dangerous, that people try to interpret former collapses of civilization as a way to convey that they are worried about today's state of the current global and Western civilization. That's something that Joseph Tenter tries not to do, because his explanation is more like structural than really context-based. Joseph Tenter is professor of anthropology and archaeology in the United States, and what he did, which was really interesting, is that he published in 1988 a book called The Collapse of Complex Society, where we analyze more than one collapse based on the idea, and let's give you the conclusion straight of his way of thinking, is that the root of collapses of many complex societies are because of the diminishing returns on the efforts to solve problems, including problems of resource supply. And the way of solving problems needs energy consumption, thus the need of integrating energy into the equations. Before we go on, Joseph Tenter is warning the readers against what he calls the progressivist bias. And as an anthropologist, he remarks that we have to be very careful about what he calls ancestors' myths, which are that for us, civilization is created through progress, and that's something that is cultural state of our civilization, which could be falsely applied to former civilization or former process to understand how they worked. And it's not because something is culturally normal that they are structurally or naturally normal. And the kind of ancestral myth which is very prevalent according to Joseph Tenter is that innovation are low energy capture, and as we will see afterwards, Joseph Tenter is not of that opinion. The other ancestor myth which Joseph Tenter tries to combat is that surplus energy precedes and facilitates the evolution of complexity. And as we will see, complexity plays an important role on how society thrives or maybe fall. The problem with the progressivist bias, the idea that progress, science, innovation, efforts, heroic facts, and involvement of people in society can cause a society to rise, is that innovation is in fact not really constant in human society, in human history especially. There has been periods with a lot of innovation and other with absolutely none. In the long history of the human race, there has been a long stretch of time where innovation disappeared and tools that were created were no longer in use. So the idea that progress is like a monolithic idea which would flow through different generations could be put in doubt. And the other idea, the other problem with that view is that energy surplus might have drove cultural evolution, and this is true, especially with the fossil fuel eras. But that might not be true beforehand, because we don't have the proof that energy surplus have been the norm in the history of mankind. It's more like the contrary. The other and last counter-argument to the progressivist point of view is that complex society are very costly. In the history of mankind, the productivity of labor is decreasing as we try to involve more people per area of land. Thus, the idea that the complex society would have existed beforehand because of just innovation and pure benefits is contradicted, because it would have costed much more for not direct benefits to people. Complexity bears a cost to people and impose constraint on them. Thus, it should have some kind of benefits that really direct their action. And Joseph Tinter shows that the idea that progressivism led the development of civilization might be not true. So we will see that, and as it is a presentation of his work, then it will be interesting to have the physicist's point of view about that, if that makes sense or not. So as we saw, energy surplus are not really important in history. They are actually very rare. But somehow in our civilization, we really value complexity and what it is and how it is used especially. And the idea that we value complexity might actually prevent us to understand how collapses unfold and what are the structural causes to collapses. And this is the reason Joseph Tinter tries or proposes to ask not why do society rise and fall, as did Jared Diamond, but the better question is what causes societies to vary in different level of complexity. And in that view, this is the core message of that presentation. The other two, I hope, will be to introduce you to the progressivist bias and what are the implications on how we think future models. And the third, about the idea of sustainability and what does it mean if we take the Joseph Tinter framework for granted. That we will see for maybe questions. The complexity is comprised of two things in the work of Joseph Tinter. It's on one hand differentiation of structure. This is so difference of roles or institutions of the same type, and the variation of organization, and it's applied mainly about different levels of organization. And complexity is the product of either variation of organization and differentiation in structure, because having different roles is not really interesting if you cannot have control or integration or organization. And what organization variation does when it is evaluated, it inflicts, it puts constraints, social norms on people, thus making them work in a way that simplify the way information, matter, and energy flows into the system. Thus, complexifying is a way to, I will try to find my words again, to optimize a system in general. We will see just briefly the two focus of the structural and organization side of complexity. The thing to remember here is that the both work in their own realm and produce an overall complexity of structure only when they are put together. And how does complexity rise? Complexity can rise for two reasons, according to Joseph Tainter. The first one is because there is an increase of problems. As we saw beforehand, energy surplus have been rare in history, and the hypothesis of Joseph Tainter, but which is confirmed or maybe from coincidences which match various collapses of the civilization, is that this is the increases of problems and necessity for society to solve them that brought an overall increase of complexity. Thus, in order to manage it correctly, an energy influx was needed to assure the equilibrium of the system. And thus, complexity also creates further problem, because when a problem is solved and the structure has to manage various different energy influx, it is confronted to other problems, such as if you have a new problem, and he used an example of terrorism, you have to build new agencies, impose new rules, so change social norms in order to protect the society against it. Thus, for Joseph Tainter, problem solving in complex societies increases complexity. The other is less frequent and has been prevalent in our fossil fuel age, is when there is an abundance of cheap and quickly available energy. In that cases, there is what Joseph Tainter calls energy complexity spiral, where both interact and nourish each other and creates further problems which necessitate further solving, which expand complexity. When we use fossil fuels, it creates waste, it creates also pollution, which needs new solution for those problems, which in that case need also more complexity. The special contribution Joseph Tainter did in his work was to model the relationship between complexity and investment. And thus complexity can be seen as an economic function, where this is an adaptive process and levies also costs and yields benefits. The idea is that the marginal returns starts to be high, increases, then stall and decreases, and as it does, it can have a constraint on the society and in some cases leading to a collapse. Society can respond to diminishing returns in three ways. They can capture more energy, they can reduce the share of resources they allocate to various areas, or they can transform their infrastructure in order to make it less burdensome, and therefore they are not subjected automatically to collapse. But when the diminishing returns are too high and there is no more energy influx, or the energy system cannot be changed, or the structure cannot be changed, then collapses can happen. There are, in that case, rapid losses of an established level of complexity, which has been not implemented by the political structure. It is sometimes a rational scenario. We can explore that in question, especially in the case of the Roman Empire. But there are also the possibility that there is transition, especially when the system is capable of having a new energy sources or adapt to diminishing returns. There has been a historical example of that. So the collapse scenario is not automatic and an executive, definitive terminal outcome. Shortly, we will not stay long on that, but the problem with society that have high gain energy system like we have is that it's difficult in its adaptation to go to a low gain system, but those low gain system can be sustainable and assure that the complexity remains, but it needs also planning and and organization constraints, which can also eventually lead to diminishing returns. And we come now to the problem of sustainability. The sustainability means sustain the state, the desired state or condition as long as possible. This is the mainstream academic and popular view of sustainability. The problem of that view is that it might be incorrect according to Tainter, because in the popular view, you have to reduce consumption of goods in order to be sustainable, in order to let future generation have enough goods for themselves or to limit pollution. And there, if you do that in that popular view, then sustainability is automatically implemented. And that view is based on the supposition that you can reduce complexity and that it's voluntarily possible. And according to the work of Joseph Tainter, history suggests that complexity most commonly increases when we solve the problem. Thus, facing complex problems which are compounded like climate change, energy scarcity, raw material scarcity, also cyber costs increases, like we heard this morning. It might be very difficult to achieve sustainability by reducing energy consumption. We are talking about final energy consumption, not raw energy consumption. And in the view of Joseph Tainter, sustainability is not diminishing energy influxes or raw material influxes. It's the opposite. It's increasing those flows in order to allow societies to solve problems which demand an increased complexity. If we take, for instance, the regulation needed to combat climate change, the research needed, the devices or programs that are thought and maybe implemented, such as huge geoengineering programs. Those are programs which demand a constant energy flux, which we might not have for the future. This is the problem, and as Joseph Tainter shows, it might be problematic to diminish the energy flow we have in a system. And to finish, greater availability of energy per capita will be necessary for the future, especially if we want to continue problem solving, if the general overview of Joseph Tainter is right. There might be some alternative, but we don't have time to go to them. Just to finish, collapse is a normal evolutionary process. It's not a definitive outcome, and I want really to stress that there are transition scenarios that, according to his work, are perfectly feasible should the political and the energy constraint be sufficient. Second, cultures matter, and the progressivist bias might be a problem in order to approach complexity. Thus, and to finish, I'd like to let you with a Joseph Tainter question pertaining complexity and way of using it to combat to this problem. Thank you very much.
I will take few questions because of time constraints, but are there any?
Well, thank you very Frédéric Chanzan from CA Grenoble. First of all, thank you for this very nice and inspiring talk. That call for something to me is, well, what do you mean by a collapse at the end? Because you mentioned some examples. You know, you mentioned, for example, the fall of the Roman Empire. You showed the images of the Pasqua Islands, you know. And then at the end, I'm just wondering, what would be the definition of a collapse that you give? And in that sense, based on what you say, some other events that we call revolutions, where you have a drastic change in the structure of society, could it be seen as a collapse? I'm taking the example, for example, of the French Revolution, where you had a fall of what we call the ancien, the former monarchy to a new system. I'm just wondering, what is a definition? And then, finally, related to the Roman Empire, if you see it on the energy point of view, what was the source of energy? Was it slavery? What else? You know, if you could just give some insights on this, please.
I try to be quick, but the mic isn't really working. So I speak louder. The definition of collapse, according to Joseph Taylor, is a rapid diminution in social political complexity or in civilization complexity. So it means organizational complexity as well as structural complexity. And for the Roman Empire, it's really difficult to summarize it in such a short time. But the energy system of the Roman Empire was based in the first century of expansion on pillaging and plundering. Thus, they had a really high-grade system when they could acquire solar energy, which was stored in means of precious metal or valuable many goods. And then when they finished the cycle of expansions, because they had size constraints to conduct military campaigns when you are limited by the speed of troops or horses, they had to rely on low-gain energy systems, which are slavery, agriculture, where they were subjected to variation of the ecosystem, especially the solar activity, and also the trade with other nations, which was a way to balance what they had. And as soon as they lost the capacity to plunder, to acquire goods, and so we can say refined goods, refined energy in the form of fine goods, they start to have economic problems. But we can discuss that later between you and me.
So, great talk, Grégoire. I loved it, as you know. And can you go back to the Tainter's curve? Just a note, this one. This is the main feature of Tainter's model. And you may notice that it is completely qualitative. Tainter just drew it because he thought it was a good way of representing what he had in mind. But you may be interested to know that this curve can be simulated by system dynamics, with a system dynamics model which takes into account the decline of net energy available to society. And the fascinating thing is that this curve is a feature of the Seneca model. The Seneca model contains this curve. Now, we haven't published this yet, but we were surprised to find that if you plot the right parameters, you find Tainter's curve inside the Seneca model. But you find more, something that Tainter may not have discovered, that there is a second part of the curve. Because as you said, Grégoire, you could try to go back to reduce costs of bureaucracy and try to return to where you were, which is what governments try to do, reduce the cost of bureaucracy, the medical assistance, military costs. They try to go back to that through the same curve, but you cannot. The curve has a high hysteresis. If you try to go back, you go through another curve, which goes down, and eventually will take you back to zero, but going down in the diagram, and that is collapse.
From the point of physics, one could look at the society as a many particle system. And of course, in many particle systems, we do have phase transitions, which you could say are transitions to a completely different structure, which are, of course, crises, or what you would call here then this transition you're looking for. So this would change the order of the system, like you said. So this would be, from the point of physics, you could treat that as a phase transition in from solid to liquid or liquid to gas or whatever system we could look at.
I'd just like to recall, it was an introduction, and I believe it could have been better explained if should I had more time.
I would like to recommend another book, which is probably quite opposite to this one. It's by David Deutsch, who is a theoretical physicist who's been working on quantum computers and so on in the 90s, and who wrote several books, but one which I happened to translate into French, and it's called The Beginning of Infinity. And it's very interesting because it's a kind of extreme optimism about the development of mankind. But it relies, I mean, it introduces a discontinuity in the evolution of all the field of knowledge, actually, and points to the fact that there's a point where you have an opening to infinity. Like, for example, going from ideograms to alphabetic writing, or the Roman way of counting and the Indian ones, decimal thing. There's really an opening to infinity, because with a finite number of symbols, you have a combinatorial, way of doing things, and you can write any number as large as you want. There's something of its type with the Enlightenment, because it's an opening to infinity as concern the production of knowledge. And this is the key point, I think, when you think about the evolution of a society. If you block the process of production of knowledge, then you're in bad shape. Because the rule is not to have some kind of ideal, society with no problem. Problems are inevitable, point one. Point two, problems are soluble. But in order problems to be soluble, you have to have the possibility, to maintain the possibility of the production of knowledge, good explanations of what's going on. If you block that, you're in bad shape. If you leave that open, then you have some hope. And so, and I finish with that. The notion of sustainability is, game over. It's just that, and I finish. I don't know exactly the value of that, because society has never been sustainable. It has changed always. And of course, you cannot predict in what way it will change, because you don't know the knowledge in 30 years. So you don't know, So when you define sustainability as the will to maintain an order, that's certainly bad. Because if you want to maintain that, you will have to block the production of knowledge.